So the first part of this module will include resonance. And at this point, I want all of you to remember that carbon only makes 4 bonds, okay, no more. That is one of the first things that you have to remember. And in between any 2 bonds, or in between any 2 atoms, there are only 2 electrons, okay? So these are the 2 things that you have to keep in mind when you start with this module. In broad sense, when we talk about acid and base, and we will talk about acid and base during this module also, I want you to remember that all acids are proton donors in terms of Bronsted-Lowry, and all bases are proton acceptors. I want all of you to be familiar with terminologies like protons, acid, base words. So according to Bronsted, we deal with protons. According to Lewis, we deal with electrons. And we'll come back on this one more time when we actually start looking at the acid-base things. But for now, I want you to look at resonance. Now, this is a very, very important chapter, and I cannot put enough emphasis that how incredibly important this chapter will be for you, because this is going to set your basis to know how things will react. Which atom or site will attack, which atom or site will get attacked, or how electrons move. And this is the first part of our module here, where we will look at how electrons are moving. Now, when we talk about any chemical reaction, we are always looking at movement of electrons. And why does any reaction occur to begin with? If something is very reactive or unstable, they will go and want to become stable. That is the sole reason why any chemical reaction occurs. Okay? So, in resonance, the valence shell electrons shift within the molecule during a reaction. But in the resonance, the electron moves within that structure. So if you look at the example that I have shown you here, so don't think about reactions right now. Don't worry about that. We are going to look at resonance structures. Both reactions and resonance structures need electron movement. So in reactions, there are 2 structures involved. One attacks, the other gets attacked. That's the electron movement. But in resonance, the electron movement is within that structure. Now, there are certain rules that we will have to follow when we will be doing resonance, but we will look at those as we go. So the question is, when does resonance occur and why does resonance occur? To describe bonding, when you have more than one Lewis structures, that's what resonance is. When does resonance arise? Most of the time. And why is that? Resonance, again, is use of 2 or more than 2 Lewis structures to describe the bonding in a molecule or ion. Okay, so structures only differ in the location of electrons. What happens to the atoms? They stay put. What will be the actual molecule or the energy weighted hybrid? So in a resonance or in a structure, this is a resonance structure, this is a resonance structure, and then you have a hybrid structure. What does hybrid mean? Hybrid just means a combination. Okay, anything made by combining or mixing two different things or two different varieties, right? We all have hybrid vegetables, or some of the pets that we know of are hybrid. Some of the cars that we drive are hybrid. You take good qualities from other species and then you mix them together to create a better species of that part. But the two things that you have to remember about resonance is that the atoms will stay put. Any questions so far? What is the difference between a resonance and a reaction? All of you must understand this part. So in general, when we are looking at resonance, this is an electron movement, and you will have to draw curved arrows. Very important for all of you to remember. It starts from electron-rich site. Do you know what a site is? Like, for example, if we archaeologists or architects go to a site to visit and look at the location, what is the location like? So that's what the site I'm talking about. The electron-rich site, and there is the electron-poor site. When I say electron-poor, it has lost its electrons and is now a positively charged place. When we have to draw resonance or we have to show any mechanistic arrows, you will be drawing a curved arrow. It's a full arrow. It starts at the electron atom and then it ends at the atom which is electron poor. And the ending of the arrow looks like a full arrow. Remember, this is a arrow for reaction. From a more reactive side to a less reactive or more stable side. Okay, this is not equilibrium. You know, when both the concentrations or states are in dynamic equilibrium. These are not equilibrium arrows. These are not dipole arrows. When you have a dipole arrow, you have a straight arrow and then you end it with a plus sign. This is a dipole arrow. This is not a double-sided arrow also. What does this mean? The flow of your arrow will be unidirectional. It cannot jump back and forth. It's not a double-headed arrow. And it is not a double-headed straight arrow. This is a curved arrow, always starts at the electron-rich side, always ends at the positive side. If you remember dipoles, where do the dipoles go? They also go to the electronegative side. The arrow ends at the electronegative side. We will use this double-sided arrow in a few minutes when we look at the resonance structures. Okay, so please make sure that you understand that the arrows that we are going to use is a curved arrow. Electrons always move from electron-rich or high concentration, electron-rich or high concentration of place to electron-poor or low electron concentration sites. Flow of electrons is unidirectional, not back and forth. So resonance will occur when two or more than two structures have to be used to explain bonding patterns of a structure. One of the resonance structures that we have already seen is our aromatic benzene ring. Now, I want to give you an example. Let's say that I have a deuterium ion. What is a deuterium ion? Hydrogen is 1 electron. Deuterium is 2 electrons. So it is an isotope of hydrogen. Do y'all remember what isotopes are? Okay, if you don't remember what isotopes are, make sure that you go back and check on what that definition is. Let's say that I have two isotopes, and from different spectroscopies, and one of them was IR, but we cannot use IR for figuring out, but other spectroscopy like NMR or X-ray crystallography, which are highly advanced spectroscopies, it was figured out that between these two carbons, sometimes the double bond is there, sometimes the double bond is not there. And so it was figured out that two different Lewis structures were necessary to explain the bonding pattern of your overall hybrid benzene ring. And so we make a circle within this ring. This is one resonance structure. This is another resonance structure. This is your hybrid structure. You just combine these two or mix these two varieties and you have this right here. What is commonality that we see here? In all your resonance structures, you will have same connectivity of atoms. Your total number of electrons within the structure will also stay same. So this is same number of electrons. The most important thing is that the octet will be maintained. This is a rule that you can never, ever break. What does this rule mean? If carbon can have 4 bonds, it will never have 5 bonds. You cannot have a structure where you will give 5 bonds to carbon, or you will give 6 bonds to oxygen, or you break a single bond. Okay. So within the resonance structures, your octet has to be maintained for all the atoms, not just carbon. And then the overall charge has to be the same. Oops, same. So this has overall 0 charge, this has overall 0 charge. This will also overall have a 0 charge. What happens during resonance is that the structure will experience spread of electrons as electron delocalization. So the spread of electrons on all the carbons, how do we get that? And how does the electron or the structure feels that stability? Okay, we can look at that. And Nelson has asked, can we have deficient octets, like 3 bonds on a carbon and no lone pairs? Now carbon, unless you have a special case where carbon has an X and let's say all of these are hydrogens, carbon will always keep its 4 bonds. If you are given a carbon with 4 bonds, you should end up with carbon with 4 bonds. And we'll see a few examples of those. That's a very good question, Nelson. So these are the rules that we have to follow when we have to look at our structures, or when we're looking at our slide resonance structures. Okay, let me share my screen again with you. So if you look back at this molecule that we have right here, what is happening? The electrons are delocalizing or spreading out. That's what is happening. In this structure above, I'm going to draw my curved arrow. First of all, in this structure, which is the most electron-rich area? All of you, pay attention to this. Not only to the structure, but overall. Whenever you will have an electron-rich site, how will you recognize it? Right? So let's look at those rules.
Formal charge.
Very good. We need a formal charge and all. So let's make rules for that also. So when you start making your resonance structures, okay, to draw resonance structures, we need to keep our rules in mind. But you also have to start at electron-rich site. Who is the most electron-rich site? For all the molecules, a negatively charged atom will have most electrons on it. Since it will have most electrons on it, it will be the most electron-rich site. After the negatively charged atoms, yes, lone pairs. Lone pair electrons, if you have presence of lone pair electrons, which can delocalize. Now, I have specifically mentioned lone pairs which can delocalize. There are some lone pairs which will not be able to delocalize also. And the last is pi bonds. Yes, pi bonds, the double bonds or the triple bonds. Among the negatively charged atoms, among the lone pairs and the pi bonds, the negatively charged atoms will be the most electron-rich site. And I'll give you a few examples in a minute. If you look at a structure like this, okay, this is my bond line structure. I have forgotten, but I have not given it here, but you must understand this. All of these dots are carbons. All of the other bonds which are not shown here are hydrogens. This is an overall neutral molecule, and oxygen bears 2 lone pairs. Okay, oxygen has 2 lone pairs, nitrogen has 1 lone pair. So make sure you always remember that. Whenever you look at oxygen, whenever you look at nitrogen, always think about their lone pairs along with them. Among this structure, where is the source of electrons? So if you look back,
there.
Very good. If you look at all the sources of electrons that we might have, we can have a negatively charged atom, we can have a lone pair, or we can have a pi bond. Who is the source of electron here?
Oxygen.
Oxygen. Very good. If you look at structure like this, now in this particular structure, and let me put a counter ion. Do you all remember what a counter ion is? A counter ion is just a metal ion, which is a spectator ion. It has no contribution to the main reaction. It just watches. You know, when a tennis match or any match is going on in the play field, only the players are the actual players. The other people or the audience sitting there are just the spectators. They are there, but they're not contributing anything to the main play. So in this particular structure, all metal ions, just like all metal ions, the sodium ion is also a spectator ion. Just like in this structure, oxygen still has the lone pairs. But what extra thing this oxygen has is the negative charge from this metal ion. This is also something that you all have to be able to recognize. You know, down the lane, I will say, okay, sodium, something like this, right? Let's say that I say, this is what your structure is. How are you going to draw the line formula for this? You should break it out. Sodium is directly attached to oxygen, which is directly attached to this carbon. Now, carbon needs its 4 bonds. And I should have done the HDI before I started out to write the bond structure. CH3. If you look carefully to this, this is my sodium ion, O negative, CH3. This is a ionic structure. This is a ionic structure. I have the formal charge. I have the formal charge. And I think Nielsen pointed this out, that we need a formal charge in our structure. If I have to compare A and B, both of them are electron donors. This is from the negative charge, this is from the lone pair. Who will have a higher capability to give away electrons? The one who has more electrons. And in this case, it is B.
B.
Very good. Any questions so far? So you have to remember and be able to recognize what is the structure, or how are you going to see your, or where are you going to start your arrow at. Now in lone pairs also, I have specifically mentioned to you the lone pairs which can delocalize. What does this mean? It means that when this electron pair moves, sorry, the lone pair moves, when the lone pair electrons move, they should not violate octet rule. Now, what is this octet rule that we keep talking about? And don't worry, we will come there also. So the second thing, so the first thing about the resonance structures is you have to start at the electron-rich site. You should all be able to recognize your electron-rich site in the molecule. The second thing that you have to remember is that the arrow, remember the curved arrow, will end at the electron poor site. What is the electron poor site? Electron poor site is a place where electrons can be accepted readily. Okay. Examples: vacant orbitals. Which are the two vacant orbitals that we know of? One of the vacant orbitals, or where the electrons can move in, are the p orbitals of lone pair atoms. So the atoms, for example, nitrogen and oxygen, both of them have lone pairs in them. So when you're doing resonance, these lone pair electrons are not part of the bonding structures. So they are not involved in the bonding. So they are freely available. But in our electron accepting sites, the p orbitals, or the lone pair orbitals, have to be empty, not filled. These are filled with lone pairs. These have to be empty. Another example are sp2 hybridized atoms. So for now, just memorize what I'm trying to tell you. Where are the electron-rich sites? The negative charge, the lone pairs, and the pi bonds, which are your electron poor sites wherever your vacant orbitals are available. For example, sp2 hybridized atoms or empty p orbital atoms of the lone pair. Yeah. So also remember that metal ions will help you make the atom next to them negatively charged. So for example, if you have NaCN or potassium thiol or lithium CH2CH3 or sodium acetylide, just know that these are the metal ions. Metal ions are always positive. The atom next to them will hence become a negative. The atom right next to them, making them very, very electron rich. So the next is never exceed the octet rule. So now is the time that I'm going to explain to you what octet rule I'm talking about. And let's just start back with this molecule again. I'm going to redraw it in a manner like this. Now, if there was a structure like this, and if there was a structure like this, first, you should be able to identify among these two structures if this is going to do any resonance or if this is going to do any resonance. Okay, now when does resonance take place? Whenever it can. In both of these structures, the resonance cannot take place. Why is that? Let's look at this first example. This extra electron or the O negative is the electron's rich site. There is no doubt about it. But can this move to this oxygen? And how I'm going to move the electron rich site and making my carbon the electron poor site, right? Electron rich go to electron poor. If by chance I can do this, what is going to happen? Now remember each bond, remember I told you to remember this in the beginning of this chapter. Each bond between two atoms is made up of two electrons. These two electrons, if I place here, I'm going to make another bond with carbon. Right? I'm bringing these electrons right here so that I can make a new bond with oxygen and carbon. If by chance, even if I show it on paper, oxygen has its two bonds and its octet is complete, this carbon's octet is complete. But what about this carbon? Do you think this carbon has its octet complete? Or,
No.
very good. This carbon's octet is violated. The electron goes to make more bonds than necessary for this carbon. You cannot do that, and you're now violating or exceeding the octet rule. Never exceed the octet rule, but we have seen, and Nelson, this might answer your question. We never exceed the octet rule, but if we are falling short of it, that's fine. That is actually allowed. But in this particular example, if we move the oxygen's extra electrons to this carbon, 5 bonds will happen. And that is something that is never allowed. What about this? In this particular case, let's say that I do take away electrons from this and make a new bond here. Let's say I do that. Okay, let me keep my curved arrow like this. Now what will I get? I will get another bond between carbon and oxygen, right? And this bond will stay. And this will get a positive charge, this will get a negative charge. Do you think this is possible? We know sometimes oxygen does take extra electrons on it. It gives away its lone pair to make a new bond. It is allowed for oxygen. What about this carbon? Is the octet
No.
being violated or is it maintained? It is being violated, yes. So always remember, never ever exceed the octet rule. Whenever you're moving electrons, always remember a new bond will form. A new pi bond will form because the sigma bond is already there. The fourth rule that all of you must remember is avoid breaking single bonds. Now this happens, but in rare occasions. Probably you will never see it. And unless the departing molecule or unless a very stable departing atom or group of atoms form. So when we break a single bond, let's say we do break this oxygen-hydrogen bond, this hydrogen can exist as a H positive. It can exist on its own. But the rest of the molecule, we are not making it properly. So how do we go about it? Let's look at an example that I wanted all of you to see much earlier. Again, I'm drawing the ugly, incorrect, square kind of a box. Remember, whenever you are going to make your carbon chains, you should always be making them in a zigzag fashion. So ideally, I should have drawn this, but I'm going to draw this for all of us to see. Any questions so far? Am I running too fast? Okay, good. Now, halogens. Now, if you draw the Lewis structures of this molecule, the halogens have 6 lone pair electrons. But we don't consider them to be the lone pairs which can be delocalized. Remember, a few minutes ago, I had mentioned that when you start at the electron-rich site, you should have lone pairs of electrons which can delocalize. Why don't we delocalize the chlorine lone pairs? Anyone? If I do that, I will be violating octet rules. Chlorine. Can chlorine have 2 bonds? No. And can carbon have 5 bonds? No. So these lone pairs are can never delocalize just because of this reason, because they are going to just create violated octets. Okay. Now, how about this? That, oh, you think that I just want to, this chlorine at that point, carbon will have to break one of its other bonds. Okay. Why don't I do this? That I push chlorine towards here and kick out this hydrogen. Let's say we do that. Breaking a carbon-hydrogen bond takes a lot of stringent conditions. Okay, even if you feel that I can give this chlorine a positive charge and carbon can kick out this hydrogen out of it, so there are actually 2 bonds on the carbon. Look at this system. Overall, you had a neutral molecule, but now when you're doing the resonance, your structure is a positive
Different.
molecule. Mhm. So
This
here
will be
overall, it was at least overall neutral. But here, now your structure is going to be overall positively charged. So you cannot kick out hydrogen just like that, or any single bonds cannot be broken. Unless there is a good leaving group, then carbon could have done that. But still, this movement of lone pairs right here is tremendously wrong. We will study how carbon loses its leaving group, but we will do that in module 6. Yep. So for now, just remember that while you're drawing resonance structures, do not break single bonds. So keeping these 4 rules in mind, let's see where resonance structure can occur. This is page number 3. And the answer to this question is that where resonance structures occur, it's everywhere, anywhere. If resonance can occur, it will occur, because resonance helps spread electrons over a structure and helps the structure feel stable. If a structure feels stable, stabilization, do you think it'll react? It will not react. It'll just stay calm. Looking back at the 4th slide here, just want to show you how we're going to go about. So what are the 4 rules? The first is to start at the electron-rich area. Among the negative charge and just lone pairs, we know that the negative charge is the more electron-rich site. Since this is the more electron-rich site, the atom next to it is the most electron-poor site. So how is my arrow going to go? From electron-rich to electron-poor. So if you look at this same location, a new bond has formed. But this carbon, which was making 4 bonds to begin with, has this system. Okay, instead of drawing 2 pi bonds, 2 bonds here, I'm going to keep the sigma bond and I'm going to show you the pi bond like this. So from the negative charge, and please assume the rest of the lone pairs also. So from the rich area to electron poor area. And yes, the new carbon-oxygen bond does form. But this carbon has a 5th bond. So 1, 2, 3, 4, 5. This carbon has a 5th bond. Can that bond be broken? Yes, it can be broken. And from the bond to the atom, the electrons between the carbon and oxygen move from the bond to the oxygen. What happens to this oxygen then? This oxygen is now carrying extra electrons on it. So look at the new structure. This is the new structure, right? Same new structure. Overall, this was negative, this is negative. Overall, the atoms are in their place. But what has shifted? The only thing that has shifted are the electrons. From this oxygen, they have now moved to the other oxygen. Okay? Any questions from this part? I can go from this electron-rich site, break the pi bond here. So I'm just moving my electrons. The pi electrons from here are now going to this oxygen. If I go back here, the extra electrons from the oxygen went and made the new bond with this carbon oxygen. So if I look from here to here, I can go back and forth. So all of this is just arrow formalism. But what I want you to memorize, besides the 4 rules, is to look for patterns. And if you remember, we have looked at allylic systems when we were doing constitutional isomers in module 1. So looking at all of the allylic systems, what is a allylic system? An allylic system consists of 2 carbons who have the double bond and a third atom. This third atom is known as the allylic site. Allylic is the atom next to the double bond. Vinylic is on the double bond itself. So if you look at this particular structure that I have, where is my allylic site on this structure? This atom, A, B, C. This atom, the carbon atom here, is my allylic site. So if I have to say how many allylic hydrogens are present in this molecule, I will just go about count all the hydrogens, make sure that I have all the hydrogens. So this carbon should have 3 bonds because it is making the 4th bond here. This carbon should have 2 hydrogens because it is making the other 2 bonds right here. This carbon should have only 1 hydrogen because it is making the other 3 bonds right here. This carbon should have 2 bonds, 2 hydrogens because it is making the other 2 bonds right there. So among all of these, where are your allylic carbons? This is my allylic carbon. How many allylic hydrogens do you have?
2.
Yes, very good. So just like we assign the hydrogens, the halogens, the hydroxides, and other univalent atoms based on the carbon to be primary, secondary, or tertiary, we assign the univalent groups as allylic based on the atom they are on. Okay, let's try one more. Okay, tell me how many allylic hydrogens I have in this structure.
Nothing.
Go ahead and draw it. How many allylic hydrogens are there?
Nothing.
There are 4 allylic hydrogens here. Check it out. A, B. So your double bond constitutes the A and the B.
It should CC.
The third atom right here, the third atom right here, both of these, this carbon and this nitrogen, both of these are your allylic sites. And
I have
so,
question, please.
hold on, Sammy, just hold
Okay.
on. This nitrogen has 1 hydrogen. This carbon has its own 3 hydrogens. And so 1, 2, 3, 4. 4 allylic hydrogens on this molecule. 2 allylic sites, one of them is a carbon, one of them is a nitrogen, but 4 allylic hydrogens. Yes, Sammy, go ahead.
Double bond, it should between any two atoms
Any
or
two. Any
carbon, any two.
Any two.
Okay.
Look at this now. How many allylic hydrogens do I have now?
3.
Exactly. There are no allylic hydrogens here. This oxygen has this group. This is not a hydrogen. This is a carbon right here. Remember, all dots are carbons. And so there are 3 hydrogens, but this is not on the allylic site. This carbon is on the allylic site. So make sure that all of you recognize allylic and vinylic sites. Okay, I want all of you to draw the structure. So looking at this structure, how many allylic hydrogens this structure has? You don't have to answer to me right now. I'm going to start a poll in a minute. And then from there, I want you to answer that. Okay, I'm going to start the poll now. Looking at this structure, how many number of allylic hydrogens are there in this molecule? Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. And most of you did say 10. And that is the correct answer. So if you look at the allylic site, I'm going to label them as ABC, ABC. Also look at this, ABC. Right? So these hydrogens, and these hydrogens are at least part of your allylic group. The next group is right here. If you had looked at A, B, C, this is the allylic site, no doubt about that, but there are no hydrogens on it. So we cannot use that. But A, B, and C. So both of these hydrogens will be counted as your allylic hydrogen. So 6, 7, 8, 9, 10. Yeah, very good. So these patterns are something that you will have to memorize whenever there is a allylic lone pair. When I say lone pair, I don't always mean oxygen. You can also have a lone pair in form of nitrogen also, right? A, B, C. So this is also allylic site. This is also allylic site. But the empty orbitals, that's where, or the electron rich area is the one that is going to do any resonance. Okay. When we look at allylic positive charges, or if you look at lone pair adjustment charges, or when we look at pi bonds or the conjugated pi bonds in an enclosed ring, these are the patterns that all of you must be able to recognize. Okay? And before we do any more examples, let me just tell you a few more things. What if you do not see the allylic site, right? For example, when we did this example, oxygen, was there a allylic site? There is no allylic site here. So does that mean that they cannot do resonance at all? So look at these examples. What do you see here? Besides allylic sites, just like in our pattern here, one curved arrow pattern. So the structure is different of what I made here. If you look at my structure is a little different. But right here, you will be using the lone pair adjustment. Okay, so let's try, oops, sorry, my bad. Let's try to do a few examples here. So from electron rich area to electron poor area. And I will show resonance with a double-sided arrow with O. Now I will make a new bond between this oxygen and carbon. The rest of the molecule, these CH3s, stay where they are. We're not touching them. So this is one resonance structure. This is another resonance structure. Let's look at this now. How many carbons are here in the main chain? Portia Thompson, are you here? Portia Thompson, are you not here? Okay, Larion Clausel, are you here?
Yes.
Okay, can you help me count? How many carbons are in this main chain?
5.
1, 2, 3, 4, 5. Very good. Thank you, Larry.
I'm sorry, her name popped up over when you were counting them. Can you do that again?
Okay, 1, 2, 3, 4, 5. So this positive charge is on the dot. Okay, it is not on this carbon. It is on the carbon next to this one. So there is 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon. So make sure you don't make this mistake when you're looking at your structures. Now, if you look at this structure, do you see any allylic pattern? Yes, we do. There is A, B, C, A, B, C, and we also have A, B, C. But these C's are useless as allylic. They will be more of a vinylic kind of a system. So the only useful allylic site is this carbon. So let me redraw this positive charge. Now, where do I have to start my resonance structures arrow? What do I see here? I see pi bonds and I see a positive charge.
Bye-bye.
Where will I start? Very good. And I'm going to do this one arrow. We can do one arrows. If you can show your electron movement with one arrow, that's completely fine. So within the structure, what will my resonance structure look like? This part of the molecule, which I did not touch, will stay as it is. But this carbon, and this carbon have been involved. A new bond will form between these two carbons. So instead of drawing a pi bond, I'm now going to do a electron depiction. The new bond forms between these two. What happens here?
Positive.
Electron deficiency happens here. And the positive charge will come here because of that electron deficiency. Okay. What all can I do? What other thing can I do? I can use this other part to show another resonance structure. So A and B are my first two resonance structures. When I will move these electrons, I can get my third resonance structure also. So in a similar fashion, these two electron arrows, they will make a new bond right here. And this electron will become unavailable. And a vacant orbital is created here at this particular site. And hence we say a positive charge has appeared. So we have 1, 2, 3 resonance structures. Ideally, you could have shown this also, right? But in that, you will be missing out some steps. So my advice to you is only move one pair of electrons at one time. So you don't skip any of the structures or any of the steps in between. Okay, don't jump too far, especially in the beginning. Take one step at a time. Do all the skill builders after we are done with this class. And let's do one more before we jump at other parts also. Let's do this example. I didn't show it, but all of you should remember oxygen will have its lone pairs and the negative charge will have just extras. We will locate. So these two are definitely oppositely charged. But what we also see is the allylic system there. So Sammy, to respond to you, allylic systems do not always have carbons in them. They can have any atom in them. Can a movement occur at this carbon? No. There is no positive charge, there is no negative charge, there is no excess of electrons, there is no deficiency on this site. The only thing that will happen is among these three atoms, not the rest of the molecule. So the electron rich goes and makes a new bond with the electron poor, in this case, nitrogen. The nitrogen cannot make more than 4 bonds. And right here, nitrogen is making all the 4 bonds it can. So it is going to break 1 bond. Who will keep the extra electrons? The electronegative oxygen can keep all these electrons on it. What happens to the rest of the molecule? We don't even know. Or we know there might be a big bulky group here who is not even involved in the reactions. So these two are your resonance structures. Okay. Now let's also look at some wrong arrows. Let's say that we have this allylic system. How do we know which place to go to? This is lone pair, this is a pi bond, this is a lone pair. I did recognize my allylic location. I know this carbon will be not involved. Only these 3 atoms, my oxygen, carbon, and nitrogen, are going to be involved. And there might be a big structure. Don't be scared. Look at one part first. Deal with it first. Then look at the rest of the part. So I would usually draw out all my hydrogens, all my lone pairs, especially if I'm going to do any curved arrows at the beginning. So which is my most electron rich site? Let's say that I say this oxygen with the lone pairs are my electron rich site. Okay. How will we move around with that resonance? From the oxygen being electron rich, that's the first arrow that we will see. Any questions so far? Why did I draw this wrong arrow? And I'm sorry, how do I draw the arrow? Just from electron rich lone pairs to electron poor pi bonds. That's what my thinking is right now. And what if it is your thinking when you're drawing it? Now look at it. There will be a new bond forming between carbon and oxygen. Nothing with nitrogen. Do you think this will be a good idea?
No.
Remember, we cannot just break a single bond. We cannot do that. At least you have to memorize that part. You cannot just break a single bond. Unless it's a good leaving group and we are doing some stringent conditions for it. But for your course, until we reach module 6, you don't have to look at that. So this is violating our octet rule. So remember non-delocalized lone pairs. For the new bond between oxygen and carbon, a triple bond has been created, which is completely wrong. Even though you say that this is overall neutral, but the octet rule is being violated badly. Let's say I have a molecule like this. It's very similar to this, but I don't have my pi bond. There are no lone pairs. Do you think there can be a resonance in this structure where there is just a plus charge by itself? Do you think I can do this or I can do this? Do you think we can do that?
No.
No. Because even though we don't see them, there was 1 hydrogen here, 1 hydrogen here, 3 hydrogens right here. The carbon has all its octet in place. If you will want to go about here, first of all, it's wrong arrow. positive charge, your arrow will never generate from a positive charge. Never, ever. Second of all, if you can generate it, if you think you did generate it, you will get a double bond here, which will again violate your carbons bonds. 1, 2, 3, 4, 5 bonds. So when you will draw your wrong arrows also, I mean, I hope you don't draw them first of all, but if you do, please make sure that you always know when you move an arrow, what are you moving? You are moving lone pairs. I'm sorry, electrons. Okay, so after you have drawn resonance structures, all the possible resonance structures, for example, this resonance structure, there were 2 resonance structures that you drew up. And now is the time that we have to decide, let's make the hybrid of these 2 structures. One of these resonance structures will contribute more, significantly more. And so we can use the elimination method to find out the most insignificant structure. How do we do that? Significant, and insignificant. So insignificant structures, what will they have? I'm going to write that up. Most insignificant structures will have a positive carbon and a negative carbon within the same structure. How do they look like? Now remember, chemistry is nothing but opposites attraction. If one atom is positive, the other atom has to be negative. Remember when we have sodium hydroxide. In sodium hydroxide, oxygen is negative. The atom next to is positive. So, we don't have formal charges within the structure. We have what is known as partial charges within the organic molecules, because they are not like ionic molecules with metal ions and non-metal ions. These are both non-metal ions, but this partial charge difference of plus and minus is usually written as just C positive, bond C negative. But when we write our ionic formal charges, they are completely separated with no bond between them. So the most insignificant structures will have a positive carbon and a negative carbon within the same structure, and the major contributor will not have a complete octet. So what must the major contributor have? The major contributor must have a complete octet. So the insignificant one will have a positive and a carbon, positive and a negative carbon. But the significant one will have the complete octet. The insignificant one will also have separation of charges. Now, if you remember the structure, just the structure, both of these are reasonable resonance structures, right? All of them have complete octets. But if we look at this structure, there is a separation of charge between these 2 bond atoms. This has a positive carbon and this has a negative charge. Overall, it is neutral. Overall, it is neutral. But because there is a separation of charge among these 2, this is the more insignificant structure. So lesser contribution will be made by a structure where you see more separation of charges. So separation of charges by presence of formal charges. Another thing that insignificant structures have are a positive charge on electronegative atom. Now, what are your electronegative atoms? Usually you have a nitrogen and you have a oxygen. Let's say that I have to give a positive charge on my oxygen. Let's say I have to do that. Or I have to give a positive charge to my nitrogen. If I have to give a positive charge on oxygen, it will not like it. Oxygen is more electronegative. It is more stringy for its electrons. It is not a good donor. It would hold on to its electrons to itself. And so it will not want to make another bond. But nitrogen, on the other hand, can accept a positive charge to it. So if you have to compare, if you have to give, oxygen sometimes will take off positive charge. There is no doubt about that. But if you have given choices among resonance structures, the resonance structures with oxygen having a positive charge on it will be not considered a good resonance structure. So let's look at this structure, this resonance structure. And a few minutes ago, when we did the wrong arrow, I showed you that this is the wrong arrow. Just think there is a pi bond here and then there are lone pairs here. Among a pi bond and lone pairs, who is more electron donating? The lone pairs. When the new bond will form between this nitrogen and this carbon, the carbon will break a pi bond between the carbon and oxygen. Who will get the extra electrons? The oxygen will get the extra electrons. The rest of the molecule stays the same. Do you think this nitrogen will stay the same or will a charge appear here? How many bonds this nitrogen has? It always has 3 bonds. Don't forget this hydrogen. So what is the formal charge on this nitrogen?
Positive.
A positive, very good. So if you look at both of these, of course there is a separation of charge which makes it insignificant. The presence of charge on an electronegative element also makes it insignificant. So among these two resonance structures, this is definitely the insignificant contributor. Okay. Let's do another example. So these are the 3 parts that you have to look at when you have to decide which is going to be your insignificant, which is going to be your significant structure. So let's look at this molecule. How am I going to start about here? If I have to draw resonance structures, which atom is the one that I should look at first? So I have to start from the electron-rich site. Where is my electron-rich site? At this oxygen.
Yeah.
Do I see a allylic version here? I do. A, B, C. So I have a pi bond and I have a negative charge. Who will have more electron donation ability?
Negative charge.
The negative charge, very good. So I'm going to make a new bond right here. I'm going to redraw this, redraw the oxygen, and I will make my new bond right here. But what will happen to this carbon? The carbon will not be able to accommodate my fifth bond, so it will break. The oxygen carbon pi bond. Will anything else happen? Will any other movement of electrons will happen? So if you look, these three atoms were actually involved in the spread of electrons. All of these three atoms here, all of the three atoms here have this electrons delocalized over them. So going back here, if you look between these two, who is the major contributor? The second one. Can I make any more resonance structures here? Yes. All I have to do is think and look. This is just like a neutral system here. So between a pi bond and my lone pair, who will have more electron donation ability?
Lone pair.
The lone pair. The oxygen and carbon, they will make a new bond. But I will not make it. I'll tell you why. And then this oxygen will break a bond. What I will show is this oxygen actually not participating in your resonance. If you remember our patterns, I can go about with one curved, with a pi bond between two atoms of differing electronegativity. I can do that also. See that? Any questions why I did not involve my allylic site? Okay, so I can use that. So all the electrons from the pi bond will go to the O, and the carbon will get a positive charge. So I have A resonance structure, I have B resonance structure, and I have C. I want all of you to think about it and tell me which is the least significant structure among all of these three, A, B, or C. We know B is the major contributor. Why? Because it is completely neutral. All octets are complete. Overall, the charge is maintained. So which among these two
C.
is going to take the hit? Very good. And why?
Because it has an incomplete octet as well as formal charges.
Very good. Very good. So formal charges are present in this molecule also. Formal charges are present in this molecule also. However, an additional problem with this structure is that the octet is incomplete for oxygen, it is incomplete for carbon also. So only if we have to look at the significance of all our structures, the completion of the octet is more important than all the other factors. So incomplete octet makes this as the insignificant contributor. And this is your minor product. Okay. So which of the following resonance structures which I'm going to draw will contribute more? Let's draw this example. Let's do this. So there is a pi bond, negative charge. Definitely the negative charge will start to move first. Okay. And then If you look at this structure and if you look at this structure, who will be a better contributor of resonance among these two?
Second one.
The second one. Why? Because its octet is complete. Okay. So we also have to look at the lone pairs that can be delocalized. So let's look at some delocalized lone pairs. First of all, the lone pair electrons must exist in an unhybridized p orbital. What does that mean? If you look at this structure, which I'm drawing right now, these lone pairs are not part of any bonding right now. And that is what the unhybridized p orbitals are. They can and they will, because they're in the allylic site, goes and makes a bond here, breaks a bond here. Same single bond, oxygen with a hydrogen. But now oxygen and carbon are making a new bond. No new bond with carbon. This will get excess of electrons. This will get a positive charge. This is a sp2 hybridized orbital. Oxygen still has a lone pair here. Do you think now this lone pair can be delocalized? No, it cannot be. Planar structure p orbitals can overlap in the same plane, but not in a trigonal planar format. Okay, so this is a planar structure. And your p orbital cannot move here. This electron will not be able to move. So all the atoms involved, for example, the 3 atoms involved in these example, let's say, have to be overlapping for the lone pair to be delocalized. So even though we know this system is an amide, eventually this sp3 hybridized orbital will become sp2 hybridized. So only sp3 orbitals will be able to delocalize, never from sp2. A second identification is that, let's say that you have a system like this. If I have a lone pair within a ring, the lone pair of each of these, of any atom actually, any atoms, either pi bond or a lone pair can delocalize, not both. Delocalize. So for any atom, either the pi bond will delocalize or the lone pair. So if you look at this particular example, I can A, B, C. I can delocalize this particular structure. But what if I have a sp2 hybridized atom? Now my pi bonds can move, but not the lone pair. The reason is in the sp3, I have a tetrahedral system. the pi lone pair, the p orbital lone pairs are perpendicular to this plane. But in this particular system, my lone pair is within the same plane and it cannot move or overlap. It cannot be used for movement. The other lone pairs or sp2 orbitals, we can see that the electrons can move within them, but not from that part which is flat. So if you look at these sp2 hybridized orbitals, they are perpendicular to the plane where the electrons can move. But this lone pair is lying flat on the structure. So even if the electrons come, they miss this lone pair. Let me see very quickly if I have an example of that. No. Okay, I would want you to look back in your book where you will see that how the lone pairs or the p orbitals, only one of them can be available. All right, the last thing that we would like to do today is I want all of you to think if the lone pairs here can be localized or not. So among this structure that I'm drawing right now, I have shown you 3 atoms with lone pairs. You just have to tell me in the chat that which atoms lone pairs can delocalize and which of them are localized. So for example, this nitrogen, the lone pair is occupied in the perpendicular hybrid orbital and cannot be delocalized. We call it as localized lone pair. But the lone pairs which can move around, which can give their electrons away, can be called as delocalized lone pair. So among all these 3, which is your delocalized lone pair? Which atom will give you a delocalized lone pair? So just answer that, and that will be the end of our class today. Okay, I got an answer from 1 at least. Okay. So I see most of you are answering the correct answer, and the answer is only B. Only B will have the delocalized lone pairs. If we used the lone pairs from this, we will break the single bond, and we will definitely violate our octet rule. And if you look at this lone pair exists on a sp2 hybridized atom, and hence we cannot have this lone pair move at all or be part of the delocalized lone pairs.